Okay, so for a question like this, we have to understand what happens when an object falls. So I'm just going to use this example perfectly. But before that, we need to pick the key lexis in the question, and that key word is minimum energy. Now, I do not want this to block our screen, but we see minimum energy in the question. Now, they've told us the dimensions of everything and the weight of this guy. Say this guy weighs about you know what it weighs. Just gonna roll up a bit. It weighs about 4,000 newtons and rests on a flat surface. Blah 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 blah. Now, good. To determine the point where an object will roll over is when the center of gravity passes one of its diagonals. So the moment it topples, when we say it's toppled over, is when this line, this is the center of gravity here, this point is when this point here, this line of action of the weight basically crosses this line. So let's look at it. Let me draw it. Let me draw it even slanted one. Now in this slanted diagram, this is very rough. The center of gravity, you see, it's past one of the diagonals. So now it's gonna fall, definitely. It's definitely gonna fall. It's definitely gonna fall. That's why to prevent an object from toppling over, we increase how wide it is. That's why this guy will be so difficult. This guy here will be so difficult to topple over because center of gravity is so low, so it has to travel a very long distance before it can topple over, right? And with this guy, because his base is so small, because now if we look at the structure of this guy, this is the center of gravity, these are the diagonals. You see, this is one of the diagonals. You see the angle it has to pass to topple over is so great, as opposed to this guy that just has this tiny angle here. That is why one of the ways of increasing stability is to make it a wider base. Now for this question, seeing that, so we know we just need to make the line of action just touch one of the diagonals, and then there will be a difference in height, and we find that. And that's all you need for the question. We already know that this will be 0.6, right? We already know this will be 0.6. But then finding this guy is just finding the diagonals, and to find the diagonals, since we have the dimensions given, we use Pythagorean theorem. So we're finding this diagonal, we're finding the midpoint of that. So, and we have 1.2, we have 0.5. we can use Pythagorean theorem to be 1.2 square plus 0.5 square, all divided by 2, and that will give us the height from here to here, and we need the difference between this height and this higher height, and that will be the minimum energy, because this will be like basically the loss in potential energy that would now result in a topple over motion. And then for that, we find square root of 1.2 square plus 0.5 square divided by 2, and that is 0.65. And so basically this is 0.65, and then this is 0.6. Sorry, this is higher than this guy. 0.65 and 0.6. So you minus the two of them, 0.65 minus 0.6, that will be 0.05 meters. That's basically the difference in potential energy. And then you just do mg, or weight, as they've given us, 4,000 times 0.05, and that gives you 200 joules that you need to solve this sort of question. But basically the fundamental principle still remains the same, that the line of the weight has to cross one of the diagonals, and then that difference in height between those 2 points would be the loss in potential energy, as shown here. My diagram is not to scale, that is why it's a bit off, but the main principle remains the same.